Hey guys, this is Go Introduction. We're going to go over the language, the basics, and the syntax. We're also going to look at some advanced patterns and what you should and should not do when you're writing Go applications. So Go is a fairly new language. It was released on 2009 by some guys at Google. These are, by the way, the same guys that are behind Unix, so there's some powerful people behind it. Go is a compiled language, which means it's not a scripted language, and it's also not a language that needs some kind of external dependencies to run on the operating system like Java or C Sharp. So in C Sharp you have MSIL that runs on the operating system, and without it you can't run any binary that was compiled from C Sharp, even though it's compiled. Same thing with Java. Even though Java is compiled, it's compiled into bytecode, not binary. So you still need the JVM to run Java applications on the operating system. And in Go, it's not the case. In Go, once you compile a program, all you need to do is to specify which architecture and what's the operating system that are the targets. And then you have a binary, and you can run that binary without any external dependencies. Even C++, when you compile programs in C++, you still need some kind of external dependencies. So it's still linking your binary to external libraries. But in Go, everything is linked when it's compiled. So there's no external libraries, meaning this binary that is the outcome of your compiling, that's all you need to run on your operating system. And that's very convenient. Go is built with concurrency in mind, meaning it's very easy to write concurrent applications and utilize them to maximum when needed to run in parallel. Go will actually run on multiple cores when you run it, not a single thread or process. It will actually utilize multiple cores and try to make use of as much as it can in terms of CPU. Now, whenever your application is using multiple threads to access the same data, you immediately introduce a data race problem. In C++ or Java, you would solve it with mutexes. A mutex is just a way to lock a certain piece of code for different threads not to access it concurrently. You have that in Go, but the better way of doing it in Go is called channels, and we're going to cover that. So other awesome features of Go is that build times are very fast. So ultimately, that makes development quicker. Also, the memory footprint of a Go application is very low compared to other languages. So that makes it ideal for DevOps solutions and environments like microservices. So there are things that are not ideal in Go, and they will improve over time. And two of them are errors and generics. In almost any other language, you would have try catch, which is a mechanism to catch errors that bubble out of your normal flow. In Go, you don't have that. Basically, you would have errors that are values, and you can either ignore them or check them. You do have panic, which is very similar to what a thrown error would be in other languages. And there's also ways to catch that, like recover, and we're going to cover that. But it's not ideal to use them, and it's not intended to be used the same way as exceptions are used in other languages. A panic is basically a way to say, I'm stopping the normal execution of my function, and this is no longer normal, and I'm going to exit now. And generics is a feature that you have in almost any other language that has types, and that's the generalization of a type. When you don't want to specify some concrete type, let's say an array of int, you would say array of t, and I'll specify that type later. So in Go, you don't have that yet, but it's coming in August 2021 as the Go team promised, and that's going to solve a lot of problems today. So one final thing to say about Go is that Go is a functional language, which means functions are first-class citizens. It does have certain OOP concepts like encapsulation, abstraction, polymorphism, which means interfaces, and structs, but there's no inheritance. In Go, you would just do composition or some other solutions that we're going to see. So in Go 1.1, they introduced a way to manage your project dependencies using something called Go modules. Every project has a go.mod file that specifies the project dependencies, the libraries that you need. And there's a go.sum file that basically locks those dependencies so you could reproduce the same dependencies when you're building your project in a CI/CD environment. So to create a new project, I would just go to the terminal, create a folder of my project, run go mod init, full path of where this project is hosted. GitHub, and the project is created. Now it has a Go mod file that all it has is the definition of our module and the Go version that this project was initiated. Building is just as easy. So all we need to do is create a main.go file. Type package main, and we add a function main to it. Now that we have our binary, if we want to build it, all we have to do is run go build, and that's enough. So at that point, we'll have a project binary. It's called project because we're in the folder project. If I want to specify another name for that binary, I can add the -o flag. I can also build for other platforms using the GoOS environment variable and another architecture. By default, it will use the same architecture and operating system I am currently at. So now I can't read the project binary because it's built for another operating system. So to add a new dependency to the project, all I have to do is type go get and the place in the repository where it's hosted. Then the go mod file would have that dependency, and the go sum file would have a lock version of the dependency that was installed when I ran the command. So go get simply downloads a dependency into my go mod file. Go get -u upgrades a dependency that I already have. Go list -u -m all shows me all the available dependencies that I have in my go mod file. Go get -u just upgrades all the dependencies to the latest minor or patch version. And go get -t -u does the same thing, including my test dependencies. Other commands like go build are go test, which tests your code. It's just invoking your tests. Go vet, which is like a linter that checks for problems in your code, like inaccessible code. Go tool, which is built-in tooling, like profiling, if you want to profile your application for performance problems. And go get, which manages your project dependencies. Now, when you're building your Go binary, you use the go build command, and you need to specify in which directory the entry point to your application is. The Go compiler is going to know that that's the entry point because it's going to look for the package main and function main inside that package. You can also have other packages in your code, like logger config, which are referenced from that code that is the entry point. Note that functions and variables that start with a capital letter are exported. And if they don't start with a capital letter, then other packages from the outside won't be able to access that variable, so it's considered internal. So now that we've talked about Go in general, let's take a look at a few examples here live. Now, one thing to note is that I have about 15 projects here on the left, and for every save, I'm actually building all of those. And just to show you how quick the build is, on the right here, I have the measuring of how much time it took. I just saved it. And you can see it took 3.4 seconds to build 15 projects. So do the math, and it's pretty quick per project. So like in other languages, we have primitive types and complex types. The primitive types are pretty much what you're used to in other languages, like int 32, that's basically the same thing. Int 16 is the shorter version, the smaller type. Int 64, which is what you would call a long in other languages. You also have floating numbers, float 32, float 64, booleans, and a few other types. But once the variable is declared, like here, I can initialize it and string in it. And if I don't initialize it, and it's just declared, it's not going to be null or nil in Go. It's going to have the 0 value of that type. So the 0 value of string is the empty string. The 0 value of int is 0. The 0 value of bool is false, and etc. But this is only true for primitive types. Complex types are actually going to be a nil when not initialized, and we're going to see that soon. Now there's actually shorter ways of initializing variables. I can write var bstring equals hello, but I don't have to do that, because if I'm sending hello as a string into A, Go can actually infer the type from the value. So if I use colon equals, that means Go will actually understand the type from the value. This means declare A as a string. Ifs and else are pretty self-explanatory. The only difference here is that you don't write brackets. So Go doesn't have that. You have an if, an else, and regular type checking with double equal. So for loops are similar to what you would see in other languages. A regular for loop with a variable I that I initialize here, I increment it, and this is the stopping condition. In Go, you don't have while loops. So what you do have is a for with just the stopping condition. This is how you would do a while loop in Go. You just provide this stopping condition without the other clauses. If I don't provide anything to the for, then that's just an infinite loop. This would iterate indefinitely, and the only way to stop it is by doing break, returning out of the function, or closing the application. Go has simple arrays, which are variables that hold a series of values with a fixed size. The emphasis here is on fixed size. This is how I initialize an array in Go. I can also do var a of type int size 5. Notice here the size 5. Arrays is always with a fixed size in Go. Now I do have arrays with dynamic sizes, but they're not called arrays. In Go we call it slices, and they're a bit different from arrays. Now let's take a look at this example. Let me run this file. Okay, the output, you can see here, is as follows. I've created an array with 5 variables. This is inline initialization. I created an array of size 5, and I've sent 5 values into it. Then I modified the second element to be 25 instead of 20. And you can see here that A was 25 on the second element. Now, I can also declare a variable B of type array of size 5 without initializing it. Because this is an array and it has a fixed size, so there are going to be 5 values inside this array. But I haven't really said what those values are going to be. So the values are going to be the 0 value of the type of the array. So this is an array of size 5 of type int. So every one of those 5 values that are going to be inside this array are going to be ints. And the 0 value of int is 0. So there's going to be 5 zeros in this array. Now slices work similarly to arrays, and a slice is, like we said, an array without a fixed size. So if I create a slice here and I don't initialize it, it's going to be empty. Then I can initialize this slice to be a slice of 4 values. I basically put 4 values inside the slice. And then I can put more values inside that slice, and it will automatically resize. Now adding values is done with the append keyword. How append works is it takes a slice as a parameter and one or more elements to add to that slice. To understand how append works, you need to understand what a slice is. Now there's no magic here. A slice is basically an array under the hood, and Go will hold a pointer in that object, the slice, to an underlying array, and it will also track the size of that array and the capacity of it. What that means is that if you add elements which are more than what you already have in your array, go and create a new array under the hood and copy all those elements into that new array. So that's why you need to use the append. because when you're appending, you're actually creating, maybe behind the scenes, a new array. Now, accessing the array or slice is also very easy. If you know Python, then you would recognize this method of selecting a subset of the array. So here I take elements 2 up to 5, which means the third element, the fourth element, and the fifth element. So you can see here that if S was these elements, then I took elements 2 to 5. I can do up to 5 or 2 and on, and so on. Ranging over the array or slice is done in the following way. I have the range keyword, and using it, I get two variables. One is the key and one is the value. Now I can range over any collection, and we'll see other collections in Go, but here the key would actually be the index and V would be the value. So in this case, I'm iterating over S, which is an array, and sorry, it's a slice, and I'm printing each key and each value. So index 0 is 0, index 1 would be element 0, index 2 would be 70, index 3 would be 0, index 4 would be 60, and the last item would be 70 as well. Now let's look at maps at Go. The syntax for maps is kind of strange, but this actually specifies the key and the value in such a manner that the key is enclosed with square brackets and the return value is coming after that. I can also have complex maps like a map of string that returns a map of string that returns a string. So in this case, I have a single map in which the key is a string and everything that comes after that is the return value. Each value would be a map that gets a string and returns a string. So here we have a map that gets a string and returns an int. I've declared it here and I've initialized it within the function. Now the initialization is very similar to how I would initialize an array. Here I have a map that I've declared and initialized in one go. And the key would be string and the return value would also be a string. Now I can modify elements within the map by accessing the key. Also delete members of that map by sending the map itself and specifying which key I want to delete. And ranging over that map is also very simple, and it's done the same way we've seen before. In this case, our key would be of type string, and the value would also be a string. By the way, if I don't want to use both of them, I can ignore the key by using an underscore. Or, if I'm only taking the key, I don't have to take the value at all. Structs are very similar to objects in other OOP-oriented languages. In this case, I've created a struct. Now, a struct is basically like a class in other languages. Now, a struct is a type in Go, and we'll see that everything is a type. So, structs are types, and interfaces that we'll see soon are also types. Now, here we have a person struct with three properties in it, a first name, a last name, and an age. What you see here is called tagging. Tagging is just adding metadata on each property of the struct. We don't have to do it, but this would actually be very helpful if we're doing stuff like serialization. So if I want to serialize this object, once it's an object, into a JSON, then I can add information saying that this field is going to be called first name when it becomes a JSON. So I've created a person type here, and I'm initializing a person. I'm creating a person of type person, and this is how I specify the values. I'm actually filling up the values inside that person. I don't have to fill in all those. I can also create an empty person. Struct can have complex and primitive values. So one of those fields can be another struct or an array. Like in this case, we have an animal struct, which by the way, I've defined inside the function. I don't have to define the types outside the function. And I am initializing the entire animal struct right here, sending the array and the name property. Then I can also iterate over this this array, the slice of animal, same way I would do before. One cool feature of Go is called promotion. So because I can have a complex type inside of a struct, so let's say I have the animal struct, I wanted to have an animal inside this herbivore, I could specify a field called animal of type animal. And then I could do something like herbivore that has an animal, and I'm creating an animal inside. Promotion actually lets us sort of like mix between those structs. So if I'm specifying just the type, I'm saying yes, a herbivore would have an animal inside, but the properties of the animal would also be available on the herbivore itself. So if I create a herbivore which has an animal inside, I can simply do herbivore.name. And name is not a field on herbivore, it's a field on animal. But I didn't have to do animal.name. I can do that. But because I use promotion, so the fields of animal become available on the herbivore. It's mostly used in mutexes. So once we see how mutexes work, if we wanted to protect some sort of type, then we could just simply state that this type also has a mutex in it, and I could be able to lock this object as if this object was a mutex, but in fact, there is a mutex inside it that I'm actually locking. Another cool feature is called anonymous structs. You don't have to create the type in advance. I can actually create an anonymous struct. Say, I just want a temporary object without, declaring in advance those types. I can do this. Now, we would be able to add fields dynamically. This is especially useful for tests when you don't want to have cumbersome types and declaring everything and keep things simple. Go is a functional language, which means functions are first-class citizens. So functions can also be values. In this case, I'm calling the function hello and getting the value out of it. I can also use the function as a value. So I can do a hello. In this case, it would be a function. I would be able to call a just the same way as I called hello. Now, in Go, function does not have to return a single value. Function can also return multiple values, like in this case. Here I'm returning two strings, and I'm initializing both values in one go. Go also has a keyword called defer. And what defer does is it postpones the invocation of a function to right before we exit the function that we called it from. In this case, I defer the invocation to last high, and I also defer another function. And let's see what happens. So we see here that the first three lines were hello there, hello world, and another hello world. These are these lines. And the last two lines were called from the defer statements. So even though we called defer first, they happened last. But here we had two defers. So the ordering of invoking deferred statements are reversed, like a stack. So the first defer statement would be invoked last. Second defer statement would be invoked second to last, and so forth. This is especially useful if we want to make sure that some piece of code happens before we exit the function, like resources cleanup or handling errors before crashing the application. On this example, we have an employee struct, and we're initializing the value e of type employee. And this employee has a first name and a last name. And what we want to do is print those values. So we have a function that receives a first name and last name and returns the concatenation of both. Now sometimes it's easier to do it if we could just attach a function to that struct. And the way to do it in Go is called receivers. Now a function receiver is just a way for us to define a function that belongs to a struct. In Go we don't have this keyword. So to access this object that we're referring to, we pass it along. So when invoking a function full name of an employee, like here, for the function to know the values of the object, it can access it through this function receiver. Note that by doing this, we're not really changing anything in the employee struct. If we wanted to mutate that object, we couldn't do it because this is actually sent by value. So this is a copy of the struct. If we wanted to mutate the struct, we would have to pass a reference to it. So there are two kinds of function receivers. There's function receivers by value and function receivers by reference. So this typically states that we want to change something in the struct. And this variation would indicate that we only want to get something from the struct without the ability to change it. So another type we have in Go, like struct, is an interface. So an interface in Go is also a type. An interface is sort of like a contract for your struct to fulfill. But unlike other languages, when we have interfaces and we have structs that are implementing those interfaces, the implementation is not explicit. So in this example, we have a type rectangle, and it's a struct that has two floats. And we have a function receiver called area that calculates the area of that rectangle. There's also a function receiver called perimeter that does a similar calculation. Here we have a shape S, and a shape, to remind us, this is an interface. What we can do is we can declare a variable S of type interface shape, and we can put a rectangle inside that shape. We can do that because rectangle implicitly fulfills this interface. Now we didn't have to do something like struct rectangle implements shape or something like that. Go knows that this type implements the shape interface because it has the functions required to implement it. So if you think about it, this opens up the possibility to implement interfaces that I don't really know about. I can be a struct that has a certain function that fulfills an interface that is defined in some other package, and this would work. Another syntactic sugar noting here is that I don't have to specify the values of the struct by name. I can just send them by the same order that they're defined on the struct itself. Now in Go, interfaces are used heavily. The Go standard library encourages using interfaces whenever you can, and you're going to see it a lot in packages out there. Go does support some level of dynamic usage of typing. So I can use the empty interface to infer the type of I, the variable I, in runtime. Go does support dynamic usage of typing. I can use the empty interface to specify that I is a variable of any type. And I can infer that type in runtime. So I can switch on the type of I, and in case it's a string, do something. In case it's an int, do something else. And if it's none of those types, do something else. Notice how here, even though I know that I is of type string, I still need to convert I to string. So there's a shorter way of doing it. I can declare I to be of a type, and in case the type is string, then I do not need to convert I into that type because I is already declared here as a string. Same way I would be declared an int here. So Go has pointers, which are the same pointers you would have in C++. Pointers allow me to pass a value by reference, so I can mutate it. So here I have a person struct with a first name and last name that are strings. And I'm creating a person and I'm sending it to a change name function, which is going to modify the first name of that person. So let's run this function and see what happens. So in this case, I'm printing the person, Alice Doe, and then I'm sending this person to the function. And after I sent it to the function, the first name did not change. The reason to that is that most types in Go are sent by value. So Go will actually create a copy of that value and send it. If I want to send the same person, the same reference to that object, to a function, I need to use pointers to allow that function to mutate the original variable that I wanted to change. Now to send the person by reference, I need to add an ampersand at the beginning of the object to specify that I'm sending the address to that person. So this would send a pointer to person. Here we have an array of size 5, and we're sending it to a function called changeSecondItem. Now, in this example, the same thing is going to happen because arrays are also sent by value. But unlike arrays, slices are sent by reference. And the reason is that if you remember the example that we talked about in slices, so slice actually holds a reference to an array. Even though I'm sending a copy of a slice, I'm sending a copy of the slice object. So that copy would contain the same reference to the underlying array. Some types in Go are sent by reference by default, and specifically slices, maps, and channels will always be sent by reference, so there's no need to creating a reference to them and sending them to another function. The best part of Go is probably Goroutines and channels, as we're going to look at them now. So Goroutines actually allow you to invoke a function asynchronously in the background without waiting for its output, like promises or futures or even threads in Java. But Goroutines aren't threads. Goroutines are actually very lightweight constructs that are built on top of threads. So it's very easy to create many Goroutines, and it doesn't cost as much. So I can create millions of Goroutines with a fraction of what it will cost me to do the same thing with threads. Creating a Goroutine is very simple. All we have to do is add the Go keyword before we invoke a function. So in this case, we are creating a Goroutine that will run the print hi function. So basically, we're going to run this, and this will run in the background while the rest of the function keeps running. So when I run this code, I see hi and hi2 printed. This won't always be the case. If I run it a few more times, and we're going to see sometimes only hi2 will be printed. This is a weird behavior. So before we explain what happens here, let's look at another example. In this case, we have a for loop, and each iteration we launch a Goroutine that's going to print the same I variable from that iteration. Let's run this example. And here nothing was printed. Now the reason nothing was printed in this example and the one before it is because those Goroutines are launched, but the main function closes down before any of those Goroutines get a chance to run, because nothing holds back the main function and prevents it from closing before those Goroutines finish or even start. Now, one way to solve these problems is using the sync package. It has a lot of cool tools to handle these kinds of problems. One of them is the wait group. Create a variable of type wait group. We don't have to initialize it, and it has a function add, which adds to a counter. You can also use the wait function on the wait group to block until that counter reaches 0. So we decrement that counter by invoking done every time a Goroutine finishes. This actually creates the behavior for our main function to wait until all those Goroutines are finished. Let's see what happens in this example. Can you guess what's going to be printed? Okay, so definitely not what we expected, because in this case, what happened is that it printed 1, 0, 1, 0, sometimes a 3. What happened here? This is happening because when you launch the Go routine, it is referencing the same I variable that is used in the for loop. So what we need to do is actually pass I as a copy to that Go routine. One way to do it is actually just pass it as a parameter to the function, and then you're going to see a different behavior. Here we see all the numbers from 0 to 9 being printed. So the key takeaway here is to never rely on these kind of closures and always pass in a parameter to a Go routine. Even better, I could define an external function, externally defined function that receives that parameter. And here I also need to pass the work group, the weight group. So a weight group needs to be passed in by reference. So here I would have pointer to a group. Here I would pass in weight group. See what happens. And we get the correct behavior. So in Go, we have another construct called channels. Channels allow me to put data inside them and pull data out of those channels in a thread-safe way. So it makes it ideal to pass information in and out of Go. Here's an example of creation of a channel. I use the make keyword and I pass in the type of the channel. It's a channel of type int. Here, what we're doing is that we are creating a Go routine that is going to read from that channel, and from the outside, I'm going to read a variable out of that channel and print it. So the thing with channels is that they're blocking, and a regular channel, an unbuffered channel, as we'll see it in a second, they don't have any capacity to hold values inside. So if I try to put something in that channel, something else needs to come and take that value from that channel for me to continue the flow of the application. So I need some kind of Go routine in the background that will try to get values out of the channel. And at the moment that I put something in that channel, then that Go routine will take that value out of the channel. And the channels are also used for blocking, for synchronizing things in Go. Because if this is a blocking operation, then I can use it to control the flow of my code. So it's essentially a reading and writing operation from a channel will happen in the same moment. It's a synchronization matter. Now, also, if I try to read something from the channel or write from it, I will block. And if nothing else will be waiting to read or write to that channel, then this is a deadlock because nothing else in the application is running that can take that value out of the channel. So we'll see an example of it here. In this case, I have a Go routine that writes into that channel, and the function that created this Go routine is trying to read from that channel. Now, if I didn't have this part, then I wouldn't be able to read from that channel. This would essentially block. What happened here is that the code came to this point and it stopped until this Go routine reached the point where it's writing to the channel, and then the rest of the code continued. Now watch what happens when I remove this part that reads into the channel. Essentially, it would mean that I'm trying to read from a channel that nothing else is trying to write to. This would block, and it would also block indefinitely. And Go would identify that moment as a deadlock because the application would be stuck at that point. So let's see it happen. Here, Go is actually telling me all Go routines are asleep. No Go routine will ever going to wake up and free me from that lock. So this is basically a deadlock. Now what we saw so far is called unbuffered channels. I have the ability to make the channel accept a certain amount of elements until it starts blocking. So basically, if I create a channel, almost the same way I did before, but add a comma and the number of elements it should hold, then until this channel reaches this number of elements, it will not block. So in here, I create a channel, I put a true in that channel, and then I read from it. In a normal channel, an unbuffered one, this wouldn't run. I mean, this would crash because this would be a deadlock. I would try to write to that channel, but nothing else at this point reads from it, so I'm already stuck. But here, this channel was able to accept a single item, and I was able to read from it. Now, if I tried to write twice into this buffer channel, then the same problem we had at the beginning would happen again, because this channel is buffered for one item, and I'm trying to write two, so essentially this line would block. Now, another thing to note here is that nil channels are blocking. So that's just the behavior of a nil channel. I can create a channel, I can put a nil into it, and then from that point, this channel will simply block. That's how nil channels behave. So in this case, I have a nil channel, and I'm trying to get something out of that channel. And let's see what happens here. So all Goroutines are asleep. Basically, I block at this point, and there's nothing else that can help me. So this is expected. Now what I could do here is have a Goroutine run in the background and always try to read from a channel while I'm writing to it. So in this example, we have a channel, and we run a Goroutine that runs a for loop, an infinite for loop in the background, and it will always try to read from that channel and print something. And in the main function, I would write 3 values for that channel. And what we're going to see here is that only 2 values will be printed. Now this is the same reason that we saw before, that once we write values 1 and 2, this Goroutine will catch those values. And once we write 3, so the main execution will stop and this Goroutine won't have the chance to print the third value. What I can do here is that I can range over a channel just like I would range over an array or a map. And if I range over a channel, that means I would be reading items from that channel until that channel is closed. So I close the channel by using the close function, and I pass in the channel that I want to be closed. And once this channel is closed, then this range will exit. Let's see this example. In this case, I get 3 values printed. This coroutine puts 3 items in that channel, and then the original function that called this coroutine is going to range over that channel and read those values until this channel is closed. Now the thing about closed channels is that while normal channels that are open are blocking whenever you try to read from them, a closed channel will always allow you to read from that channel. So if I close a channel and I try to read from it, I will immediately get a value. What value would it be? So the value would be the 0 value of that channel. Now, if I try to write from to a channel, it would panic, meaning the application would crash. So never write to a closed channel. As a rule of thumb, the responsibility to close a channel is always to the one that created the channel. Someone who's reading from a channel should never close a channel, only the one who's producing items into it. The reason for that is that when someone's reading from a channel, it can actually check if the channel is closed or not. I get another value when I read from a channel. The first one would be the value that I'm reading. The second one would be a Boolean indicating whether this channel is open or not. So usually I would get this value and true here. But if the channel is closed, then this value would be false. And what I would get in the value itself is the 0 value of that channel. This is actually how range works. So range behind the scenes reads from a channel all the values until this indication here would be false, and that means the channel is closed. If someone who's writing to that channel would want to check if the channel is closed, there's no way to do that. So that's why the responsibility to close a channel would be to the one who's producing it and not the one who's reading from it. One final example with channels and Goroutines is broadcasting. So I can use close to actually have multiple Goroutines get a message from that channel. The message would say this channel is now closed. Now because this channel acts like a queue, there's no way to put a value into the channel and having 2 separate Goroutines read from that channel the same value, right? I would need to write 2 values into that channel for 2 Goroutines each to read that value. So if I wanted to somehow signal 2 separate Goroutines that are reading from that channel that this channel is now closed, I would do that with close. So here I have 2 Goroutines. One of them is reading from the channel and another one reading from that channel. And the outside function is writing to it. Now, once I close that channel, both Goroutines will exit the range because that channel will now be closed. So essentially, I'm closing everything, both Goroutines, by simply closing the channel that those Goroutines are reading from. What if I have multiple channels that I want to read from? If one is blocking, then I wouldn't be able to do anything else. So for that, we have the select statement. So in this example, I have one single for loop that every time some value becomes available in one of two channels, I will read a value, and the next iteration will wait until one of those channels becomes available for reading. By the way, I can do the same thing with writing, because if I try to write to a channel, it still blocks. And I also have another channel here called exit channel, that all I'm doing with it is just signaling this for loop that we don't want to continue this iteration anymore. That's why we use the empty interface here, because it doesn't really matter what the values here are. What matters is that once we write to this channel, then we know this for loop will exit. We can do the same thing by simply closing this channel if we want multiple for loops to get the signal from us. Why do we even need to work with channels when we're working with Goroutines? So we've talked about potential data races here, and they're not always obvious. But anytime two different Goroutines are accessing the same data, even if one Goroutine is only writing to it and the other one is reading, that can potentially cause the application to crash. To make it crash, I would have to have both Goroutines do this operation exactly at the same time. It won't always happen because not always Go will run those Goroutines on separate threads. Sometimes Go will run them on the same thread, but sometimes it won't. So I don't really have a consistent deterministic way of finding that out always through the code. What Go does provide is a tool called the race detector. So I can actually ask Go to check if such a situation can potentially happen. And if this situation can happen, then Go will definitely let me know about it. So Go won't always catch those cases, but when Go says that there's a race condition, then there's a race condition. Running this example normally wouldn't produce any error most of the times. But if I want to check it for race conditions, I add the -race flag. Now I get an exception saying exactly which coroutines are trying to access the same data structure. And we don't have to use Goroutines to handle these kind of situations with data races. We can also use Mutexes. Now, Mutex exists in most other languages, and it's fairly easy to use. All it does is locks a certain area of the code for only one thread instead of having multiple threads access it. So if I lock a mutex right before I write to a data structure and then I unlock it, then I can be sure that only one thread will have access to this area of the code. If all I'm trying to protect is a primitive like an int, sometimes I can use a simpler approach by using the atomic package. So for ints, for example, instead of using a manual lock and unlock of a mutex, I can just use the atomic package to use a thread-safe version of an int. So in this example, I use heavy writing and reading into the same data structure from two different Go routines. So if I run this example, see that I've read 84,000 times and written 8,400 times into the same data structure. And running it with the race flag doesn't produce any errors because this is all done in a thread-safe manner. But mutexes aren't the preferred way of doing such things in Go. Go does encourage the usage of channels. So the best way to implement a thread-safe handling of data from different Go routines is with the following example. So here we have a virtual bank. We have a deposits channel and a balances channel. We have a function deposit that takes an amount and puts it into the deposits channel. And we have a balance function that reads from the balances channel. We have another function init here, which is a feature of Go, by the way, that allows us to run a function at the startup of an application per package. So for package main, when this package starts up, or being important, this function will be invoked. So basically what we're doing here is that we have a state, and this state will be managed by this function, the teller function. And we want that every time someone would want to update this balance, then this update would happen only in a single thread. So the way to do it is to have two channels. Whenever someone would want to read the state of that bank, then this someone would simply read from the balances channel. Now the balances channel doesn't hold any information inside it, right? Every time someone reads from the balance, then we have a function that would have to write into that channel to supply that value. And that value would come from that same int that we're using to manage the state. Same thing with deposits. When someone runs the deposit function with an amount, then essentially we're just pushing into the deposits channel. Now when someone's pushing into the deposits channel, then this would block, and it would be unblocked if the teller, that function that manages the state, would immediately see that someone's trying to push into that deposits and read from it. So when someone's trying to write into deposits, that same moment for us who we're trying to read from deposits, this would be unblocked. So we would get that amount that someone just pushed into deposits, and we would use it to update the balance. And if someone reads the balance, right, so it's reading from the balances channel, this would get blocked until we come and we actually write into the balances channel the current state. So essentially, every time someone deposits or gets the balance, it's blocking, and we're catching that in real time and fulfilling that request. But this part that's reading from balance or updating it is done by a single function. Let's see that final example running. So we're seeing here two Goroutines. One is simply depositing 1,000 times. It's depositing 1. And every 2 milliseconds it's going to happen. And another Goroutine, every 200 milliseconds is simply reading the balance. So there's heavy concurrency happening around this balance here, but everything is happening in a synchronized manner. So this last example is really the most recommended way of handling data race conditions and thread safety problems in Go. I recommend checking out the Git repo with all these examples, and also an awesome site I found called Shichao's Notes, which really shows how to do things properly in Go, and there's a lot of cool examples here for you to look at. So that was Go Intro. We went over the basics and some cool patterns you should use when working with Go, and I hope you enjoyed. Let me know if you have any questions.